Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover coordinates and change of basis. Linear algebra. So let B be v1, v2, all the way up to vn, be an ordered basis of vector space V, and then let vector x be a vector in V such that x can be written as a linear combination of those basis vectors, so c1, v1, c2, v2, all the way up to cn, vn. The scalars c1, c2, up to cn are called the coordinates of the vector x relative to that particular basis. So we can write this in coordinate form like we would in any algebra or calculus class, that x is going to be, this vector x would be equal to c1 comma c2 all the way up to cn. Or I could write this vector x in a vertical matrix. So let's kind of talk about the standard basis and what we're accustomed to. So let the coordinates of this vector x be 5, -2, 4. For the standard basis b, 1, 0, 0, 0, 1, 0, then 0, 0, 1, then we know that c1 being 5, c2 being -2, and c3 being equal to 4, these are the coordinates of that vector because I can write this vector as a linear combination of these bases. Moreover, it's 5 times the first vector, in that basis, minus 2 times the second, plus 4 times the third. And if we simplify this through vector addition and scalar multiplication, this thing simplifies exactly to this piece here. So I can also write this in a vertical matrix as 5, -2, 4. So x, with respect to, let's say, this basis, we usually call this the standard basis, so let's say s. So this vector with respect to s is going to be equal to 5, -2, 4. Now, let's do an example where I'm going to turn, I want to rewrite the coordinates of a vector in terms of the standard basis. So if the non-standard basis b, we'll call it b prime, is 1, 0, 1, 2, and we can actually prove that's a basis, and I did that in a previous video. So this is a basis of R2. And I've given you the coordinates for this particular vector. These coordinates are going to be 3, 2. Now these are the coordinates over top of this basis. So I want to determine the coordinates of this vector relative to the standard basis. And let's say, I'll leave it as b, but we usually call the standard basis s. So what I know is since these are the coordinates over this basis, then I can say, this vector x is going to be a linear combination of c1, which is that 3, multiplied by the first basis, plus 2 multiplied by the second basis, because that's why they say this is, an ordered basis, that this 3 will go on the first vector, and this 2 is going to be the scalar component of the second vector. So when I simplify this thing, we can scalar multiply first, so 3, 0, plus 2, 4. And then finally simplifying this is going to be equal to 5, 4. So I can also write this as, this vector x over the standard basis. I should say s, but I've labeled it as b. The standard basis is going to be equal to 5, 4. And we know for the very same reason as I could write this as 5 times this first vector in the standard basis plus 4 times the second vector. So, really what we can say is that let's write it this way. So kind of moreover, I can say, 5, 4 over this basis b is equal to 3, 2 over the basis b prime. So what I want to do now is I want to work backwards. I want to give you a vector in R2 over the standard basis, and I want to be able to write it as the coordinates of a non-standard basis. So here's our second example. It says if x is this vector 1, -2, 1, our coordinates using the standard basis, I want to determine if the coordinates of this vector relative to this non-standard basis. Now, what we know is that these are the coordinates with respect to, this basis right here. So I can write this as, 1 times this plus 2 times this plus 3 times this. But really what I'm trying to do is I want to be able to write, this vector in terms of this basis. And the coordinates of this basis are going to be the coefficients that go in front of all of these vectors, because that's what we said, that the coordinates are simply this linear combination. So really what I'm trying to do is I'm trying to find, a C1, C2, C3 such that I can write it as a linear combination of this new basis, that we have C1 times the first basis plus C2 times the second basis plus C3 times the third basis. And I want this to be equal to this vector with respect to the standard basis, which is going to be equal to 1, negative 2, comma 1. Now we know that we can do this with matrix algebra. So the first is going to be this. The first column is going to be the first basis. The second is going to be the second basis, and the third is going to be the third basis. And I need to multiply this by C1, C2, C3 is going to be equal to the output I'm looking for, which is 1, negative 2, 1. Now I can write this into augmented form if I want to just use row reduction to solve this. And then when I row reduce echelon form this particular matrix, I am now going to get essentially the standard basis here, along with the coordinates C1, C2, C3. So this is going to be 5 minus 8 and then 2. So that means that the coordinates of these things being this, I can say that x relative to this non-standard basis b prime would be equal to 5, negative 8, and then 2. And remember, we could check that. I could put these coordinates inside of this linear combination, and it will spit out this number. So we could check it using what we did previously. All right, I wrote it this way as opposed to just going straight for the augmented form, because there's a way that we can go from one basis to another basis through simple row reduction, and that's because it's tied to an inverse. So really, if I wanted to find C1, C2, C3, I really just have to multiply it by, I have to multiply this by the inverse of this particular matrix. So what I have is I have some matrix P right here, and then multiplied by this matrix C. Let's call it X, is going to be equal to this matrix B. So another way of saying this X, or the C matrix, X would be equal to simply, P inverse times that B matrix. So I could actually find the coordinates through matrix multiplication instead. Now, how would you find this inverse? Well, if you wanted to do this by hand, what you would do is you would set this up to where we have our basis b prime over here. This is going to be 1, 0, 1, 1 minus 2. Let's try that again. 0 minus 1, 2. And then finally 2, 3, 5. And then you would, join it with this, the identity, which happens to be the basis of S. And then when we row reduce echelon form this, what you're going to get here is you're going to get the identity back for this, joined with, well, P inverse. So when we get back, let's make this a little bigger. We have 11 ninths, negative 4 ninths, negative 2 ninths, minus 1/3, minus 1/3, 1/3, and then the last is going to be minus 1/9, 2 ninths, and then finally 1/9. which is going to be this matrix, P inverse. So another way of actually finding this coordinates, I could say that, x of, over the standard, non-standard basis would be equal to this P inverse right here. I'm just going to say P inverse. That's going to be this matrix right here, multiplied by this vector, will indeed be equal to 5 minus 8, 2. Okay, so what I'm trying to get to is how do you go from one basis to another basis through simple matrix multiplication? Well, this is the way we set this up. You put basis B prime over here, you put basis B over here, you row reduce, and then you're going to get what's called a transition matrix. So let me write that up, and then we'll verify that this one. So the transition matrix from B to B prime, so let B be this basis V1, V2 all the way up to Bn, and then B prime be U1, U2 all the way up to Un. Then the transition matrix from B to B prime is this P inverse, and it's found by just Gauss-Jordan elimination. You just adjoin B prime with B, and then you row reduce, and you're going to get I over here, and then the transition matrix that goes from that B to B prime. So let B be this basis negative 2, 1 through 2, and B prime be the basis 1, 2, and negative 1, 0. First, I'm going to compute this transition matrix from B to B prime, and I'm going to use this transition matrix to rewrite this relative to the basis B prime. So first, let's find that. So if I want to compute B prime, I have to go from, P inverse. I have to put B prime first. B prime being this matrix over here, or these vectors over here. So 1, 2 is the first basis, negative 1, 0 is the second basis. Now I'm going to join it with B, which is going to be negative 2, 1, and then 3, 2. Now I'm going to row reduce echelon form this Gauss-Jordan elimination, and what we're going to get is we're going to get the identity on this side, and P inverse, which is going to be 1/2, 1, 5/2, negative 2. So what that means is our transition matrix P inverse is simply this matrix, 1/2, 1, 5/2, 2. Now B asks us to rewrite this vector, which is in terms of this basis, relative to this basis instead. So these are the coordinates relative to B. I want to know the coordinates relative to B prime. So I know I can do that simply by matrix multiplication. So what we know is that P inverse times, this matrix X is going to be what we're trying to find. So P inverse being half, 1, 5/2, negative 2, multiplied by 6, 3 is going to give us, so 3 plus 3, which is 6, and half of 6 is 3 times 5 is 15, minus 6, which is going to be equal to 9. So really the claim is what I just found is these are the coordinates relative to B prime. The claim is that 6, 9 relative to those basis B prime is equal to 6, 3 relative to the basis B. And actually, let's just check just for consistency, or at least completeness. I'm going to check this. So what it means to be a basis is that 6, 9 relative to B prime is going to be, a linear combination of these bases where the coefficients, or your scalars, are going to be 6 and 9 respectively. So 6 times 1, 2 plus 9 times negative 1, 0. Now we know we can write this relative to the standard basis just by simplifying this by matrix addition and scalar multiplication. So 6, 12 plus negative 9, 0, which is going to give us negative 3, 12. And then I'm going to do this with this one as well, is that these are the coordinates, or the scalar components, or the coefficients of that linear combination using B. So this should be 6 times, the first vector, plus 3 times that second vector. Better simplify to be the same thing. So let's check. So this is going to be minus 12 comma 6 plus 9 comma 6. And indeed what we get is minus 312. And remember, this is relative to that standard basis. In both cases, this is minus 3 times, the first base of the standard basis, and then 12 times the second basis. Okay, so the real question that students ask is like, why do we actually need this stuff? And when I want to go from one basis to another basis, this can be helpful, like in signal processing. If I'm sending a signal, sometimes you get interference or some kind of distortion. So sometimes you're trying to send something, but what it's done is it's distorted it through a different basis, and you get components back that are not quite the components that you actually, want back. So you might get these, but you actually wanted these. So what you can do is you can undistort this by multiplying this by a matrix, and essentially clean up your signal and put it back. One more example, and just kind of off the cuff here, is video games, for instance, is kind of a nice spot where you see vectors all the time. And when you look at like water, for instance, you see a reflection of the scenery ahead of you, and that reflection really is just a transition matrix that goes from, well, if I want to reflect this over the y-axis, I know that my my standard basis that we're using for the world is going to be 1 comma 0. Well, let's just do this in 2D. 0 comma 1. Now, if I want to reflect everything over that y-axis, what I could use is I could use this basis instead, which just multiplies all the y's by -1. So what you could do is you could feed all the vectors that were in this basis and turn them into vectors using this basis, and then what it'll do is it'll flip all those things over that y-axis and make your life a lot easier. So the last thing I want to talk about is just simple coordinates of just like non-Euclidean vectors, and that'll take 1 minute. So these coordinates, this works for all our vectors, and they don't have to be Euclidean vectors. What if I'm talking about the P4 space? So this is a vector in polynomials of degree 4 or less. And what I could do is I could write this with respect to its standard basis, that this P is equal to, well, this is just a linear combination of this standard basis. So we have 5 minus 3, 1. Oh, actually, I have missed one because there is no x here, so there is 5, 0, minus 3, 1, 7. So those are your bases because, again, we have no coefficient for x, which means that linear combination would have to be 0 for that particular component. And say M2 by 2 matrices has this as a standard basis, and I could write this x also in terms of a column vector of 3, minus 4, 1, and 5. So, if you like the content, please subscribe.